Now that we have covered the basics of autodiff, in this following section, I will talk about how to make inferencing and training of neural networks as fast as possible in SLAM. Recall in the previous section, we defined this network parameters type to represent a fully connected feed-forward layer. We can use it to construct multi-layer networks. For example, here we are using 2 layers to implement an extremely naive neural texture. Now let's zoom in and see what computation is happening inside a single fully connected layer. For simplicity, let's consider a very simple layer that takes 3 inputs and computes 2 outputs. To compute the first output, we will compute the weighted sum of inputs using weights W00, W01, and W02, and add a bias value on top of that. And the code doing this computation is shown on the left. Following that, we are going to apply an activation function on the computed value as the final output. Here we're using the ReLU activation. Similarly, we use the same steps to compute the second output. The difference is that this time we're going to use a different set of weights, W10, W11, and W12, to compute a weighted sum, and add a different bias to the output. The initial result is then going through the same activation function to produce the final output value. Now let's ignore the activation part a bit and just focus on the weighted sum computation. If you look carefully, you will find that the computation here is exactly a matrix vector multiplication followed by a vector add. The weights form a 2x3 matrix, and the input is a 3-element column vector. And this is a super useful observation because we have a lot of tools to speed up matrix computations. To put this in code, we will first define the arrays to hold the network weights and biases. Next, we define the eval method, which takes an input array. The output is initialized to the biases. And then we add a vector resulting from the matrix vector multiply to the output for the weighted sum part. And finally, we apply the activation function to each output and return. Now, we know that the GPUs typically run a lot of threads in parallel to achieve high performance. Assume you are evaluating a neural network that represents a neural texture. In this case, each thread is querying the texture with different texture coordinates, encoded as different input vectors. On the other hand, the network weights and biases are exactly the same for each thread, because it is the same texture that we're sampling from. This means that if you look at what is being computed across the entire wave, we're effectively computing a matrix-matrix multiply, where the weights matrix is output size by input size, and the input vectors from all the threads form another matrix whose size is input size by wave size, which is 32 on NVIDIA GPUs. So when all threads are computing the same eval function here, the GPU as a whole is effectively computing a matrix multiply followed by an element-wise add. This operation is called matrix multiply accumulate, MMA, also referred to as general matrix multiply, or GEM. This is important because modern GPU features dedicated hardware to speed up the small matrix multiply add operations. For example, NVIDIA GPUs has the tensor-core hardware that can compute matrix multiply add very efficiently. However, when you use the tensor-core to do the matrix multiplication, all your shader threads will operate cooperatively to compute the matrix. This means that your shader needs to explicitly switch to cooperative execution from traditional SIMT execution mode during the MMA calculation. The hardware-accelerated MMA operation is exposed in various graphics APIs. In D3D12, they are referred to as the wave matrix intrinsics. On Vulkan, they are made available through the cooperative matrix extensions. On Metal, they are exposed as SIMD group matrix intrinsics. As we just mentioned, MMA intrinsics isn't the easiest thing to use from shaders because they assume a cooperative or SIMD program model instead of the more flexible SIMT program model that all shader code are written against. Because of this, the shader is restricted to call MMA intrinsics only from uniform control flow where all the threads are active. For example, you can't call the matrix multiply intrinsic from an if-else branch. In addition, you must explicitly pack the input vectors computed from each thread to a shared memory location, so you express the computation explicitly as a matrix-matrix multiply in your shader code. To solve this problem, we are now given a new way to access the same MMA hardware, and this is called cooperative vectors. Cooperative vectors are available in D3D12 shader model 6.9 and in Vulkan via the NV cooperative vector extension. The similar concept is also available in Metal 4. Basically, it enables you to write the shader code as a normal matrix vector multiply, and it will map your code to the MMA hardware automatically without needing you to explicitly pack the vectors into a matrix or requiring the computation being initiated from a uniform control flow path where all threads are active. Recall our previous implementation of the fully connected layer. It is a matrix vector multiply followed by an activation. We can simply rewrite this function to use cooperative vector intrinsics like this. The key difference is that we replace the inputs and outputs from a float array to a coop vec. You can think about a coop vec exactly as an array or an ordinary vector that doesn't have the size restriction. And we call the coop vec mat_mal_add to do the hardware accelerated MMA. Here in the intrinsic call, we are specifying the input vector, the address to fetch the weights and biases, and also with some additional arguments that define memory layout of the weights matrix. Here we are specifying a simple row major layout and a 16-bit float encodings for the matrix components. There are many other layout options that are more efficient, but we will leave this part to the next section of the course. One thing to note is that we're using 16-bit float for the weights here. You may be tempted to use 32-bit floats for simplicity, but please don't try that because they are not supported by most GPUs for coop vector intrinsics. But apart from that, it is just as this simple to use cooperative vectors to speed up neural network inferencing. If you are only doing inferencing in shaders, this is all you need. The nice thing about cooperative vectors is that they can also be used to speed up training neural networks too. To implement training, we need to address two issues. One, we need a place to store the gradients of weights and biases. And two, we need to make this eval method differentiable so it can be integrated with the remaining code through autodiff. The solution to the first issue is easy. We just add additional fields to point to the memory location that we can write the gradients to. Making the eval function differentiable is a little more involved. We have two challenges here. One is that the built-in coop vec type isn't considered by Slang compiler as the differentiable type. We are still working on making coop vec a differential type out of box, but for now this is not yet the case. Second, the coop vec mat_mal_add intrinsic is not a differentiable function either. Since coop vec type is not yet considered differentiable by the Slang compiler, we need to wrap it into a differentiable type. Here we define the ML vec type that conforms to the idifferentiable interface. The type simply wraps a coop vec for data and implements the required dadd, dmal, and d0 method to make itself differentiable. This is all just boilerplate. Again, the Slang compiler should soon support coopvac as a differentiable type, so this boilerplate won't be needed once we are there. With the wrapper defined, we can simply change our signature from coopvac to mlvac. Now, let's make the eval function differentiable by providing a custom derivative function. By Slang's autodiff rules, backward gradient propagation function of eval should take a differential pair of mlvac as the first parameter, and a result grad parameter representing the gradient for the output that needs to be propagated backwards. This function is required to do two things. First, it needs to propagate the gradients from the result grad to the network parameters and store them in weights grad and biases grad. Second, it needs to propagate result grad into each input vector element and return them via input.d. Since the eval function is essentially computing a matrix vector computation, we will simply follow the mathematical rules to derive it. These are the math details that you don't have to understand right now, and we will just use the conclusion here. Given an MMA computation, U equals to MV plus B, where M is the weights matrix, B is the bias vector, V is the input vector, and U is the output vector, the equations for computing dm, db, dv, and du are given here. I'm not going to derive the math now, and you don't need to understand the details to understand the remaining implementation, so just trust me that this is correct. What is important to understand is that the workload on the GPU will look like. Recall that during an actual inferencing session, each thread is computing its own output vector from its own input vector, but they are all accessing the same weights and biases. This means that during training, the gradients are going to propagate into the same memory location holding the gradients for weights and biases. In practice, we will implement this as atomic adds so that the gradients propagated from different threads can be correctly accumulated into the same memory location. Fortunately, for each term that we need to propagate gradients into, there is a corresponding coopvac intrinsic to do exactly that. To propagate the gradients to the weights matrix M, we will call coopvac outer product accumulate to compute the outer product of du and v, and atomically accumulate the resulting matrix to dm. For biases, there is the coopvac reduce sum accumulate function, which atomically accumulates du to db. And finally, to compute dv, we use the coopvac matmauer function to do the transposed matrix vector multiplication. Here is how it looks like in code. First, we're going to we will backprop the result grad through the activation function. Then we call the coopvac outer product accumulate to backprop the gradients into weights. Here, note that the coopvac outer product accumulate requires the gradient of weights being stored in training optimal layout, which is a vendor-specific opaque layout. So if you want to read the values of the propagated gradients afterwards, you will need to convert it into a row measure or column measure layout in a separate step. We will talk more about this in the next section. Next, we will call the coopvac reduce sum accumulate to propagate the gradients into the biases vector. And finally, we use the coopvac matmauer to do the transposed matrix vector multiply to get the gradients for the input vector. Note that here we achieve the transposition of weights by specifying the layout to be column measure layout, where during inferencing we were specifying row measure layout. Once we made the eval method differentiable, you will be able to integrate with other parts of code that are automatically differentiated. Here we can simply mark our neural textures sample method to be differentiable, which will allow gradients to propagate from the loss all the way to the network parameters. With this, we can just use the type in a training loop the same way as we discussed in the previous section. The only difference is that now the core computation of the neural network training is accelerated by the tensor hardware. To give you an idea of the performance improvements using the cooperative vectors, here's a benchmark of training a neural texture from a 100 megabyte PNG image. When compared to a highly optimized implementation that doesn't use co vectors, the co vector implementation is achieving a 3 to 4 times speedup depending on the GPU, which is very impressive. And that concludes this section. Now you've learned how to use cooperative vector to speed up neural network inferencing and training. Again, I would like to direct you to the resources accompanying this course for more details. You can find an end-to-end cooperative vector inferencing and training example, including the full definition of the MLVec wrapper type, by going to the MLP training coop-vec example on our course page. In addition, you can check out NVIDIA's Neural Shading SDK, which provides a more comprehensive library in Slang that implements the coop-vec accelerated neural network inferencing and training. Next, we will have Alexei to talk about the performance considerations of using cooperative vectors.